Good morning all, my name is B. Santhosh Kumar, Assistant Professor, Institute of Aeronautical Engineering. My subject is image processing. Today we are discussing about sharpening frequency domain filtering. So before going to the sharpening frequency domain filtering, we have to discuss what is the frequency domain filters. So frequency domain filter, it is a digital image is converted from spatial domain to the frequency domain. In the frequency domain, image filters are used for image enhancement for a specific application. A fast Fourier transformation is a tool of the frequency domain filtering to convert the spatial domain to the frequency domain. And smoothing is an image. A low filter is implemented, and for sharpening is an image. High pass filter is implemented. When both the filters are implemented, it is analyzed for ideal filtering, Butterworth filtering, and Gaussian filtering. So frequency domain is nothing but a spatial domain filtering is spatial domain is converting into the frequency domain. So how many types of frequency domains are there? So with the help of fast Fourier transform, we are using fast Fourier transformation tool for the frequency domain. We are converting the spatial domain into the frequency domain. And what are the types are there means low pass filter and high pass filter. So here I am using low pass filter is a smoothing filter and high pass filter is a sharpening filter. So what is the use to using these filters? Means the filters are implemented to analyze for ideal filtering, Butterworth filtering, and Gaussian filtering. Suppose spatial filter is converted into the frequency domain filtering. Frequency domain filtering. So these frequency domain filterings are two types. Low pass filter. Second one is a high pass filter. So in this low pass filter, smoothing, high pass filter is a sharpening. So the frequency domain filtering is converting the low pass filter and high pass filter. Low pass filter is also called smoothing filter. High pass filter also called sharpening filter. So this frequency domain I am using as a fast Fourier transform. Fast Fourier transform we are using here. So in this fast Fourier transform is a tool is using for the frequency domain filtering to converting into the spatial domain to the frequency domain. So these frequency domains are two types, smoothing and sharpening. Smoothing is also called low pass filter, sharpening is also called high pass filtering. So it is one example for low pass filter. So it is image which I am using low pass filter. It is the image which I am using high pass filter. So what is the difference means? Here brightness is very high. Here brightness is very low. So these are exactly opposite to this one. So when I am using brightness means whitish is very high, brightness is very high. Here brightness is very low. So inversely proportional of low pass and high pass filter. Depends on my requirement of the image, I will use low pass filter or high pass filter. Suppose any of the image I need to improve the brightness. So then I am using for the low pass filter. If I need brightness is reduced, then I will go for the high pass filter. So depends on image presentation or image transformation, we are using our application, image application we are using. You can see here it is a waveform. It is like this. It is a low pass filter. It is an exactly opposite. Here like this, it is like this. Okay, it is a high pass filter. So these are the exactly inversely proportional. It is the coordinators are U and V. here are the coordinates are u and v. H of u comma v is the output image, low pass filter image coordinates. So it is the origin. Oh, so here also it is the origin. So here it is one example of low pass filter and high pass filter. So it is one example, a two-dimensional low pass filter, result of low pass filtering image, a two-dimensional high pass filter, result of high pass filtering of the image. These are the input images and the output images. These are the example for low pass and high pass filters. So a high pass filter is used for passing high frequencies, but the strength of the frequency is lower as compared to cutoff frequency. So sharpening is a high pass operation is frequency domain. A low pass filter is also standard forms such as ideal high pass filter, Butterworth high pass filter, Gaussian high pass filter. So edges and sudden changes in gray levels are associated with high frequencies. So to enhance and sharpening significance details, we need to use high pass filters in the frequency domain. It is one example, one equation for low pass filter to a high pass filter. Capital H of HP of u comma v equal to minus 1 HP. It is a low pass filter of u comma v. So this equation is came from this theory. A high pass filter is used for passing high frequencies, but the strength of the frequency lower is compared to the cutoff frequency. So sharpening is a high pass operation in the frequency domain. As low pass filter is also a standard form such as ideal high pass filter, Butterworth high pass filter and the Gaussian high pass filter. So edges and sudden changes in gray levels are associated with high frequencies. Thus, to enhance and sharpening significant details, we need to use high pass filters for the frequency domain filtering. So here one example of low pass filter, it is to a high pass filter. So you can see here H of HP means it is a high pass filter. So the equation for a high pass filter, capital H of HP is equal to u of u comma v. These are the coordinates, two-dimensional, and it is using to 1 minus H of LP. So I'm subtracting, total value is 1. It is an ideal one. This ideal one 1 minus low pass filter H of LP of u comma v. So when I'm subtracting from an ideal number 1 minus H of LP, this value is equal to the capital H of HP of u comma v. It is the equation for high pass filter with related to the low pass filter. It is one example for origins, input image and output images. It is one original image, that is I am calling as an input image. Okay, so it is a Butterworth high pass filter. It is one output image of Butterworth. It is a Gaussian high pass filter and it is an ideal high pass filter. So there are different types are there. We are looking like these are the different are there. So when I'm using the, it is a original image with a normal, but when I'm using for the Butterworth, Gaussian and ideal pass filters like this, what is the differences means the brightness is very increased. Why? Because when I'm using this high pass filters, that is called applied the mask. Here I applied the mask technique. Here we are using a mask technique. So that is the reason of mask. The images are using as a very brightness is very low. So it is looking like a some blackish color. Why? Because we are used mask is applied to this original image. So there are the different types of images with mask, Butterworth high pass filter, Gaussian high pass filter, ideal high pass filter. So it is the another one, ideal high pass filter, IHPF. The IHPF cuts off all low frequencies of the DFT, discrete Fourier transform, but maintain the high ones that are within a certain distance from the center of the discrete Fourier transform. So what is the equation for high pass filter with the help of discrete Fourier transformation technique? Capital H of u comma v means I'm using two-dimensional. So if it is 1, what will happen? If it is 0, what will happen? So capital H of u comma v, the output image H of u comma v equal to when it is 1. When it will become 1 means it is the if d of u comma v is greater than d naught. If it is 0, when it is 0 means if capital D of u comma v less than or equal to d naught. So there are two conditions for ideal high pass filter. So when H of u comma v equal to 1 means it is an ideal condition. When it is an ideal condition means if capital D of U comma V greater than D naught. When it is not ideal means when it is 0, it is a non-ideal condition. So here D naught is the cutoff frequency and capital D of U comma V equal to square root of U minus n by 2 whole square plus V minus n by 2 whole square. It is a cutoff frequency with the help of ideal high pass filter I am using here. So it is one example for ideal high pass filter, ideal high pass filter, ideal high pass filter of an image, ideal high pass filter of a radial cross section. It is a filter and it is an image and it is a cross section. It is a cross section of the image. So when it is ideal means h of u comma v equal to 1, then d of u comma v is greater than d naught. When it is 0 means if d of u comma v is less than or equal to d naught. So ideal high pass frequency when I am using discrete Fourier transform technique, here I am using. So another example for sharpening frequency domain filters. Then here ideal high pass filter I am using. Here ideal high pass filter sets to 0 all frequencies inside a circle of radius d naught while passing without attenuation all the frequencies outside the circle. The figure below shows the result of applying ideal high pass filter with the cutoff frequencies of 15, 30, 80. So here ideal frequency with cutoff frequencies I am applying here. In the previous we are not applied any cutoff frequencies. Here only cross section area, only image, only filters were used applied. But here ideal high pass filter sets to 0 all frequencies inside a circle of radius d naught while passing without attenuation all frequencies outside the circle. But here the below figure shows it is the input image. That is the input image with that is also called original image. Input image is nothing but a original image. But here B to D, what is happening? Here figure B, figure C and figure D. But what is happening here means there are cutoff frequencies are applied here. Here what means? Cutoff value is 50. Here cutoff value I am taking 30. So in the for the original image, what is the cutoff value here? 15. Figure C cutoff value is 30 and figure D cutoff value is 80. So for the different cutoff frequencies, the looking like image is different. Okay, it is compared to B, C, D, the brightness is very increasing. Why? Because we are applying the mask techniques applied with the cutoff frequencies. So we can see the following effects of ideal high pass filter. So what are the types are there for the following effects of ideal high pass filter? First one is a ringing effect. Second one, edge distortion, that is a distorted thickened object boundaries. And the third one is a both effects are decreased as the cutoff frequency is increased. So ringing effect is one type, edge distortion is another one. So what is edge distortion means? Distorted thickened object boundaries. Here both effects are decreased as the cutoff frequency is increasing. When cutoff increasing, what will happening means both effects, this ringing effect and edge distortion are decreased. When it is decreased means cutoff value is increasing. Then the Gaussian high pass filter GHPF, the Gaussian high pass filter with the cutoff frequencies at a distance d naught is defined as. So what is the equation for Gaussian high pass filter d naught? Here capital H of u comma v equal to 1 minus e power minus d square of u comma v by 2 d naught of 2. It means 2 d naught whole square. It is one example for Gaussian high pass filter. It is image A with filter. Image B is the image. Image C with radial cross section. So when I'm using Gaussian high pass filter, so what is the image and what are the filters and what are the cross section areas are like this. Okay, so u comma v are the coordinates, that means 2D, and h of u comma v is a function. What is the value of h of u comma v is equal to, it is a Gaussian high pass filter. I'm applied the Moscow technique here. So it is the high pass Gaussian filter. Next, figure B, Gaussian high pass filter with the image condition, with the mask condition. What are the coordinates? U comma v. Why? Because it is a two-dimensional image. And figure C, GHPF radial cross section. It is a radial cross section. D of U comma v and H of U comma v. Two dimensions, two coordinates are there. So figure C is also called a radial cross section. It is another example of sharpening frequency domain. So the figure below shows the result of Gaussian high pass filter with the cutoff frequencies 15, 30, 80. It is the original image. It is the cutoff frequency 15, cutoff frequency 30, and the cutoff frequency is 80. So there are three different cutoff conditions are there. Original image with cutoff 15, original image with cutoff 30, original image with cutoff 80. So these are three different conditions with the cutoff I applied for the Gaussian high pass filtering. So it is the original image, B, C, and D figures are the cutoff frequencies were applied to the Gaussian high pass filter with the mask technique is applied. But figure B, cutoff frequency is 15, figure C, cutoff value is 30, and figure D, cutoff value is 80. So for different conditions we are used different cutoff values we are applied here. It is a sharpening frequency domain filter with the Gaussian high pass filter. So what is the transformation technique we are applied? Means fast Fourier transform technique we are applied to converting the Gaussian high pass filter. So another equation for sharpening frequency domain filtering. So it is the equation for sharpening frequency domain filtering. So the spatial domain is a domain to get the inverse transformation, that is converting to the frequency domain. The spatial domain equation we are converting inverse proportional to the spatial domain, that is the frequency domain. So in this spatial domain, what is the equation? Means S of spatial domain equation, S of x comma y equal to I dash of x comma y plus R dash of x comma y. So it is the spatial domain equation. Spatial domain equation. So what is the output? G of x comma y equal to exponential of S of x comma y. So what is S of x comma y is the spatial domain. So we are applying the exponential form to the spatial domain. That is, we are going to the frequency domain technique. So exponential of, in the place of S of x comma y, I am taking I dash of x comma y into exponential of R dash of x comma y. So here I naught of x comma y into R naught of x comma y. So what is I naught and R naught here? Where I naught of x comma y is the illumination and R naught of x comma y is the reflectance components. Okay, when I am taking the two dimensions, that is I naught and R naught. So I naught is a illumination and R naught is the reflectance of the image. So this method is based on the special case of a class of systems known as homomorphic system. Okay, so the overall model of the block diagram we're looking like I said, it is the input equation, input image f of x comma y, logarithmic function, fast Fourier technique, h of u comma v, inverse fast Fourier. It is a fast Fourier and it is a inverse fast Fourier transform, exponential function, and getting the g of x comma y. So how many transformation techniques we are applied for the f of x comma y to the g of x comma y. So here f of x comma y is the input image. This f of x comma y input image, I am applied the logarithmic function. For this logarithmic function, I applied fast Fourier transform. After the fast Fourier transform, we are applied capital H of u comma v function. It is a output function, or Fourier transform function. also called transformation function. It is also called transformation function, capital H of e comma b. It is to inverse fast Fourier transform to the exponential function, that is a g of x comma y. So f of x comma y to the g of x comma y, what we are applied? Logarithmic function, fast Fourier transform, and transformation function, inverse fast Fourier transform. For which one I am applied? For the Fourier transform, exactly opposite, inversely to the fast Fourier, that is the inverse fast Fourier transform, exponential function, g of x comma y. So here you can see exponential function I am used. Exponential function why I am using for? I am getting the g of x comma y. Before the g of x comma y, what is the final equation means? We are applying the inverse fast Fourier transform with exponential function. That is the output function g of x comma y. So here what are the coordinates I0 and R0? I0 is the illumination and R0 is the reflectance of the components. So here another one, filter in the frequency domain technique. So what is the filtering in the frequency domain technique? The basic steps for input image f of x comma y to p is equal to 2m minus 1 and q equal to 2n minus 1, and arrays are of same size if function f of x comma y and h of x comma y are the size of m into n and k into l respectively, and p, it is the zero pad function of h of h comma p. And here I am taking some values, m equal to n equal to 512, kl equal to 16, p equal to q equal to 1024. Here I am taking some values. So it is a multiply equation, and it is for equation for input function with m values, m point. That if I am taking the 2 dimension, 2k point. If I am taking 1 dimension means k points. Okay. Here one example, a discrete function of m points and its Fourier function, and a function with a discrete function of twice the number of non-zero ones, and it is a Fourier spectrum. These are the 4 equations, 4 figures are there. First one is a discrete function of m points. Second one is a Fourier spectrum, and the third one is a discrete function with twice the number of non-zero pads, and last one is the Fourier transform with m points. It is one example of low pass filter and high pass filter, means smoothing and sharpening of the filters. Okay, these are the functions of filtering and frequency domain filters. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.